To this problem 2.5.4 we have bone with bolt and clevis. Diameter of the rod is 15 mm, diameter of bolt 12 mm, diameter of washer 20 mm. So temperature of the clevis is Tc 10 mm and temperature of wall is 80. Tb is 45 megapascal, alpha is 12 into 10 to the power minus 6 degrees Celsius inverse. Modulus of flash is 200 GPa. The number 8, temperature drop resulting in both shear and stress is E is equal to alpha del T and stress is to sigma is equal to E into alpha into del T. Rod force P is equal to E into alpha del T into pi dr square by 4. The bolt is in double shear with resist. Tau is equal to P by 2 into AS is equal to implying tau is equal to P into 2 pi by 4 dB square. Tau B is equal to by pi dB square into E alpha delta T pi by 4 dr square. Tau B is equal to 45 MPa. Temperature drop del T is equal to 2 tau B into E 100 alpha dB by dr whole square. Applying del tau is equal to 24 degrees Celsius. P is E alpha del T into pi by 4 dr square is equal to 200 into putting the values we get P is equal to 10 kilonewton. Normal stress in the rod is sigma rod is equal to P 1000 by pi by 4 dr square, implying sigma stress in the rod is 57.6 megapascal. Now coming to bearing stress in bolt and clevis, sigma BC is equal to P by 2 into dB Tc in 10 by 2 and 12 by 10, which gives us 42.4 megapascal. Washers at wall delta B and P by pi by 4 into dn square minus dr square, implying the sigma bn is equal to 74.1 megapascal. Now coming to see if the connection to the wall that B is changed to an end plate, what is the required of each bolt. So delta is 38 degrees Celsius and the allowable stress is 90 megapascal. So delta T is 38 degrees Celsius. P is E alpha delta pi by 4 d square. So P is equal to 100 into pi by 4 into 15 mm square into 12 into 10 to the power 6 into 38, which gives us P is equal to 16.12 kilonewton. So each bolt carries 1/2 of the force, hence dB is equal to 10.68 mm. Now coming to second problem 2.5.6, there is an ACB bar with two solid circular cross sections held between two rigid supports, 150 mm, 170 mm, 225 mm is the length of AC and BC length is 300 mm. We have to find out the compressive force P in the bar, maximum compressive stress sigma C, and displacement del C at point C. So given LR 225 mm, D150 mm, E6 point GP, increase in temperature del T is equal to 30 degrees Celsius. Now thermal expansion due to change in temperature, delta is equal to L alpha del T. So delta is equal to L alpha AC into alpha del T plus LCB alpha del T. Putting the values we get delta is equal to 1.575 mm. The cross section is fixed at both ends, so deflection due to compressive forces del P is equal to PL1 by EA1 plus PL2 by EA2. Area is pi D1 square by 4 and pi D2 square by 4, and putting the values we get del P 0.225 into 4 by 6 into 10 to the power 9 pi into 0.05 square plus 0.3 into 4 6 into 10 to the power 9 pi into 0.05 square P. So equating del T and del P, we get P is equal to 51.775 10 to the power 3 Newton. So the compressive force is 51.975 in 10 to the power 3 Newton. So maximum compressive stress del C is equal to P by A. So stress in AC bar is P by A1, which gives us 51.75 into 10,000 into 4 by pi into 0.05 whole square, which is 26.36 MPa. Stress in CB bar, similarly on solving we get 11.71 MPa. So the displacement del C at point C is del C is equal to 4 into delta T minus PL1 by EA1, and putting the values we get del C is equal to minus 0.31 mm, which means minus shortening of region at C. Now coming to the next problem 2.5.10, there is a brass sleeve S fitted over a steel bolt and nut and is tightened. So here's the free body diagram. This is the length L, this is the brass, and this is the sleeve D1, D2. So DB is 25 mm, S1 is 26 mm, D2S is 36 mm. So compressive stress on sleeve 25 MPa, alpha S is 21 10 to the power minus 6, and alpha B is 10 to the power minus 6. So alpha S is greater than alpha B, so brass will undergo tensile force and sleeves will undergo compression. So overall expansion sleeve, so overall expansion in sleeve is equal to overall expansion in brass. So L alpha S del T plus minus PL by ACS is equal to L alpha B del T plus P into L by ABEB. So del T L alpha S minus alpha B is equal to PL by 1 by ACS plus 1 by ABEB, and on solving we get AS is equal to 486.7 mm square and AB is equal to 530.66 mm square. Now putting the values we get del T is equal to 34 degrees Celsius. Now coming to the next problem 2.510. So there's a free body diagram of ABCD. A, B, C. There's a TB tension force in cable B, TC force in cable C, D. 2B, 2B and B is the length. We have to find out the allowable load P if temperature rises by 60 degrees Celsius and each cable has factor of safety 5 at least against it. So from table AB is equal to 76.7 mm square, E is equal to 140 GPa, delta 60 degrees Celsius and AC 120 mm square. So equation of equilibrium, delta Ma equals to 0. So TB into 2B plus TC into 4B minus P into 5B is equal to 0. So 2B plus 4TC is equal to 5B, equation number 1. Compatibility equation, del C is equal to 2 del B. Force displacement and temperature displacement relation. This is the displacement diagrams. This is the displacement of point B and displacement of point C. So del B is equal to TBL by EAB plus alpha del TL. Del C is equal to TCL by EAC plus alpha del TL. Substituting equation 3 and 4 into 2, we get TCL by EAC plus alpha del TL is equal to BL by EAB plus 2 alpha del TL, implying 2 TBAC minus TCAB is equal to minus E alpha del TAB AC. Now substituting values into equation 5, we get TB346 minus TC765 is equal to 1333800. Now solving 1 and 6 simultaneously, we get TB is equal to 0.2404P minus 3840, TC is equal to 1.1253P plus 1740. Solving 7 and 8, we get TB is equal to 4096 TB plus 13.5, TC is equal to 0.887, TC 1546. Allowable load is equal to from the table 102,000 Newton, TC is 231,000 Newton. Factor of safety 5. TB allowable is equal to 20,400 Newton, TC allowable is equal to 46,200 Newton. From question 9, PB is equal to 4.096 and 240 is equal to 95,700 Newton, and from equation 10 we get PC is equal to 39,500 Newton. So cable C governs and hence the P allowable is 39.5 kilonewton, which is the answer. Thank you.